Recording, yay, I think, right? We
Yeah.
are recording. Okay,
Big
cool.
Four.
Yes. All right, guys. So with today's stuff, let's talk a little bit of business real fast. If I can pull up, I think. Okay. So all right, we did yesterday. We did I went through again on 9B here, and I put down everything that was optional, everything that was mandatory. Okay. So we did mandatory day one. That's stuff we need to know. We're doing day two right now. Okay, it's absolute convergence and ratio test. We're doing that today. And then that's going to be it. That's really honestly the last new thing that we're doing. It's the last lesson, it's the last everything. Okay, that is mandatory. It's going to be on your AP exam. So the rest of the week is going to be yours to get caught up on all this stuff if you need to. I put down here mandatory day 3. Okay, so this is a review day. I kept the same review, but I wrote down the problems. All right, the problems that you can do, that you're able to do. Okay, so you can spend tomorrow working on this review. You can spend tomorrow rewatching these videos, trying the homework problems, doing whatever you need to in 9B. Okay, so is there any questions about how any of that stuff works? I will hold office hours tomorrow from like 11 to 12, same time as now. If you have any questions, and I can do that throughout the whole week if you want me to. I really don't care. I'll just kind of pop in and we can say, hey, and if you have questions. If not, then we'll just not do it.
What are we gonna do about our textbooks?
Oh man, that is so far down the list of things to think about. I have no idea. Eventually taken back to the school, but I'm sure we'll get more information towards the end of the year about that. For now, just hold on to them. Oh yeah, also too, per request up here, if you have not joined the new Remind link, there's the new Remind link. Okay, and here is the new updated manual. Did we see the updated manual? Some nice food's ready. Oh no, don't open the internet. So if you, yeah, I took off a few topics on this one. So if you look right here. Oh, that's weird. Enable editing. Yeah. So it's down to 15 topics and you can read through those. Okay, so it should have everything that we have learned that's on the AP exam on there. Okay. So instead of 18, I think it has 15. And as far as the due date goes, I don't know. I got to figure out. It's going to be towards the end of the year, okay? Towards the end of the semester. It'll be a grade to help you, okay? I know that much. I'm not going to grade it as strict as I have been just because of the mess we're in. But yeah, not giving us any direction about grading yet, so I'll let you know. Okay. Any questions before we start the lesson? All right, let's start. Okay. So, again, if I start to my audio starts to mess up, just shout at me because it means I'm covering up the mic because my screen is you can see my screen's kind of up right now. If you see my video, so I have to kind of brace it as I'm writing. So that's kind of where the issue is. So anyway, let's start. All right, yesterday we learned the alternating series test for convergence and divergence. So there's really only one more thing that we need to know for the AP exam that they're mandating us to know, and that is the ratio test, which is right here. Okay. So what this lesson is about is the ratio test, how we use the ratio test for convergence and divergence, and then the application, another application of ratio test is how to identify an interval of convergence. Okay. And it's that piece that becomes optional. So it's at that point, like yesterday, where you can stop listening if you really want to, but I'm going to continue with it because I think it's important. Okay, so I'll kind of let you know in the video, kind of at the point where it's not on the AP exam. Yes, not Stacy. Yes, Delaney, what's up?
So the interval convergence, was that one of the manual topics too?
It was one of the manual topics for, we did it, I don't know if I kept it for power series because we already learned it. Yeah. And technically that's what we're doing today. We're still talking about an interval of convergence for a power series. It's just a little bit more in depth with the ratio test. So yeah, I can't remember if I kept it on there or not because I kept the stuff we still learned, but anyway. Yeah. All right.
Okay.
So the following test is useful in determining whether a given series is absolutely convergent. Absolutely convergent. Now that word right there, think of absolute value. So that's saying if the summation of the absolute value of a sub n is convergent. Okay. Because here's the thing, if the absolute value of a series is convergent, okay, then the non-absolute value part of it is also convergent, okay, because we learned that from the alternating series test yesterday. So this is kind of going along with that as well. All right. Here's basically what it says. This is just, again, another test for convergence, and we'll talk about the types of equations that we can use it on later. It says if the limit of a sub n plus 1 divided by a sub n, so the absolute value of that, and this is the generic case, it says if the next term divided by the previous term is, if that value is less than 1, then the series is considered absolutely convergent and therefore convergent. Okay. If the same limit to infinity of the next term divided by the previous term is greater than 1, or if it equals infinity, then the series diverges. Okay. And if it equals exactly 1, then the ratio test is inconclusive and no conclusion can be drawn about the convergence or divergence. So if it equals 1, you would have to do another test. Okay. But yeah, so this is your slide. This is your note slide. This is the notes for today. And then the next few slides is going to be showing examples of how that works. Okay. So hopefully it'll all make sense as we're doing it. All right. One thing I wanted to clarify real fast is the difference is pretty much what absolute convergence means. Okay. I'm gonna write a definition here.
Could you go back to the?
Yes, absolutely I can. I'm sorry. I'm gonna write a definition for the next slide. It's just gonna be a couple things here and just something I want you to kind of know. So we can kind of move forward. And I think Shreya, did you say that? Are you good? Are you good?
I still need a little bit of time.
Yeah,
Sorry.
you're fine. You're fine. You're fine. Just take a second. Okay. So, yeah.
Hold on.
So if we can take the absolute value of a series, all right, and it's convergent, then that's considered to be absolutely convergent. So like if you take the absolute value of something that's alternating, for instance, and it's convergent, then it's going to be convergent for the absolute value as well, or the negative part as well. Let me show you with an example. Y'all let me know when I can move on.
I'm good.
Okay. All right, look. So let's look at a definition real fast. Definition. Conditionally convergent. Okay, that is like the opposite of absolutely convergent. Okay, it states if summation of a sub n is convergent, but not absolutely convergent. Okay, let me give you an example. How about the alternating harmonic series? The alternating harmonic series, if you remember, is just the summation n equals 0 to infinity of harmonic series is 1 over n. The alternating harmonic series is -1 to the n over n. Okay. Now we showed yesterday, if you remember from our notes yesterday, using the alternating series test, we showed that this is convergent. Okay, we showed that was convergent. Now, to be absolutely convergent, all right, is if I were to take the absolute value of that, if it still remains convergent. So for instance, like if I were to take the absolute value, so n equals 0 to infinity of the absolute value of -1 to the n over n, then that simply just becomes, if you take the absolute value of an alternating series, it gets rid of that -1 piece of it. It all becomes positive. And so taking the absolute value of an alternating harmonic series just becomes the harmonic series. And we know from doing a bunch of proofs and talking about this with P series that this is divergent. Okay? So what that means is that the alternating harmonic series is only conditionally convergent. Conditionally convergent. Okay? And that's the cool thing about the ratio test, is the ratio test can determine if it's absolutely convergent. Okay? And that's more so beneficial if it's like an alternating series or something like that. Okay? So if you ever see those words pop up, that's the difference between absolutely convergent and conditionally convergent. Is if you can figure out something's convergent all day long, but if you can take the absolute value of it and it still remains convergent, then it is absolutely convergent. Does that make sense? Okay. Just make a note of this. I've only ever seen this pop up a couple times, but this is just going to help with today's notes, and so I don't have to explain the whole thing. The limit as n is approaching infinity of 1 plus 1 over n to the nth power. Like if I take this limit to infinity, the weird thing is that equals e. And I will let you look up that proof on your own, but that's going to be helpful for a later example. So I just want to keep that in mind. Okay. All right. Is there any questions about, and that, again, that's just a random limit I just need you to kind of know for today's notes. It doesn't really pop up like ever again. But is there any questions about conditional convergence versus absolute convergence? Okay, I kind of need y'all to know that. Okay, now let's actually start looking at examples of using the ratio test, now that we got that behind us. Okay, all right. It says to test the series, blah, for absolute convergence. Okay. If it asks for absolute convergence, then you should be thinking, okay, that is the ratio test. Okay, the ratio test for absolute convergence. Okay. Now, we know what the ratio test says to do. Okay, so I'm going to kind of write it out piece by piece for you. It says to do the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. Okay. And notice how when we're taking this limit, we're taking the absolute value of it. Okay. So taking the absolute value of it is actually getting rid of the alternating series piece of it, right? So can we agree that I don't even need to put that into this limit, right? Because the absolute value is just getting rid of that alternating series part. Okay. So how this looks, this is equivalent to the limit as n approaches infinity. A sub n plus 1 is the generic next term. Okay, so instead of looking at the series with n plugged into it, we looked at the series with n plus 1 plugged into it. So that's like saying n plus 1 cubed over 3 to the n plus 1. So that's the generic next term. Okay, I plugged in n plus 1 in for the n, and it says to divide that by a sub n, which is just my original series. Okay.
Was it like a beeping or like a...
Any question? I'll give you a second to write that down and think about it. All I did was do a sub n plus 1 on top divided by a sub n. And if we can show what this limit is equal to, then we can determine if it's absolutely convergent or not. Meaning that if I take the absolute value or not, it is going to converge to a value. Okay, there the sum is.
How
Go ahead.
come when you did the absolute value, it got rid of the alternating series?
Alternating series does this, right? Okay. What the absolute values is doing is it's saying take all of your negative values and make them positive. So now instead of it looking like alternating, it's going to look like this. Okay.
Okay, and those are like that's a sequence, right?
Yeah. It's of the sequence. Yeah, absolutely.
Okay.
So we're taking the absolute value, which gets rid of the negative. Now, I'm going to erase that. All I'm concerned with is figuring out this limit, okay? And it's going to be very, very procedural. It's going to be the very same steps every time. So this is going to be the limit as n approaches infinity, absolute value, and just same change flip. So it's going to be your n plus 1 cubed over 3n plus 1. And then change to multiply and then flip to 3 over n cubed. Okay. Now we got to simplify that and then figure out what the limit is as n approaches infinity. Okay. I'm going to continue my steps down here. All right. This is going to be, because we're doing n plus 1 versus n, this is going to be a very common way to simplify it. 3 to the n plus 1 is the same thing as saying 3 to the n times, 3 to the n, oh my God, why is it doing that? It's erasing everything. 3 to the n times 3 to the first, right? Wouldn't you agree? Okay, I just split up the powers. And then we notice it can simplify to this. We can say the 3's cancel. You agree? Any issues there?
Wait.
Oh wait, no, this was I'm sorry, this was 3 to the n right here. I apologize. Is that what you're saying, Lisa?
Yeah.
That should be 3 to the 3 to the n's cancel. I apologize for that, guys. I forgot to write the n last time. So we're left with just 3. The 3 to the n's cancel because I forgot to draw the n right here in the step before. All right. So when the 3 to the n's cancel, I'm left with the limit as n is approaching infinity of the absolute value of, on top I'm left with n plus 1 cubed, and on bottom I'm left with 3n cubed, right? Okay. Now, if I want to take the limit of this as we approach infinity, this is nothing more than just a rational, and we have taken the limit of rationals to infinity all the time. The leading power on top is going to be n cubed. The leading power on bottom is 3n cubed. So because we have the same powers on top and bottom, that means the limit as I approach infinity is equivalent to the leading coefficients, or just 1/3, right? The numbers that are in front of n cubed. That makes sense? So 1/3 is less than 1. And by the ratio test that we talked about in the first slide, if the limit is less than 1, then that means that the series, all right, from the original problem, the series is absolutely convergent. Okay, so I'm going to say, therefore, I'm not going to rewrite the whole series, but I'm going to say the series is absolutely convergent. The reason is because getting rid of the -1, all right, taking the absolute value, I'm showing, so anytime you have a series, if, this is kind of like a little statement here, if the absolute value converges, then the alternating series converges as well, okay? And what we just showed using the ratio test is that the ratio between the next term and the previous term is always going to be less than 1, meaning it's always decreasing, okay? And therefore, will converge to a specific sum, okay? And in this case, I don't know what the sum is. I just know based off the ratio test that it's going to actually converge to a value. So the series is absolutely convergent. Delaney, what's up?
So on the exam, I don't know if we'll do the thing where you have to write out your work or what. But when we're writing that, if we write, do we have to write therefore like actually write out the series, or can we just write the series as?
I would definitely write this out. Yeah, write that out.
Okay.
It's just really hard for me to write with this pen, and
Yeah.
also for sake of time, I'm not. But you're absolutely right. I would say therefore, and then I would state the series from the very beginning is absolutely convergent by ratio test.
Okay.
Okay. And then your work is all the proof you need. Okay, just say therefore by ratio test, the series is absolutely convergent. And you're going to see as we do these examples, they're all very much the same. Now it says test the convergence of the series. Okay, it doesn't say test the absolute convergence. It just says test the convergence. So again, what I was planning on doing was giving you a whole worksheet full of these. Okay, and you would have to decide when to use the ratio test. If you ever see like a factorial and like a power of n, that is a very common like, hey, do ratio test, especially if you see the factorial and they're asking if it converges or not. It's more than likely going to be ratio test. Okay, so there's your ID. There's your ID for ratio. Okay. Now, it's not too bad. Okay. We know what the ratio test looks like, and I'm going to kind of skip to a certain step every time. Like, what's going to happen is the limit as n is approaching infinity. Okay, and it's a sub 1 or a sub n plus 1 divided by a sub n. So I'm going to go ahead and write a sub n plus 1 first, which is n plus 1 to the n plus, I hate when it does that, n plus 1 power, divided by n plus 1 factorial. So that's your a sub n plus 1. And instead of dividing by the term, I'm going to go ahead and do the same change flip, if that's okay. So I'm going to say multiply by, and then flip it to n factorial over n to the n. Are we okay with that? That is the same thing as saying a sub n plus 1 divided by a sub n. Okay. And now we just got to simplify it. Okay, simplify it and talk about the limit as n is approaching infinity, because right now we can't really see much. Right? Here's the good thing. Okay, so if you ever see like an n plus 1 power, okay, like right here, that can be split up to, all right, let me try to squeeze this in here. N plus 1 to the n times n plus 1, right? I just split it up like I did the last example with 3. I did n plus 1 times n plus 1. N plus 1 to the n times n plus 1. Can we see that? I know my handwriting's got awful, but there we go. Okay. Now, another thing that simplifies, okay, is how can n plus 1 factorial be simplified? Well, we've talked about simplifying this before in the past, but we can break it apart because n plus 1 factorial is the same thing as n plus 1 times n minus 1 times n minus 2. Or another way of saying that is n plus 1 times n factorial. Okay. We had a whole discussion about that in the previous lesson, but if you have questions about it now, please don't hesitate to ask. It's just that I'm taking out, if it's like having 5 factorial is the same thing as 5 times 4 factorial. I'm just taking out the starting term. Okay. So with factorials, if you have n plus 1, you can break it apart that way. If you have n plus 1 in the power, you can break it apart the top way there. Those are the 2 common ways to simplify these problems. Okay. And that's going to be helpful because if you notice now the n factorial and the n factorial cancel, an n plus 1 and an n plus 1 cancels. So all this simplifies down to is the limit. Now on top, I'm left with just n plus 1 to the n. And on bottom, I'm left with just n to the n. Okay. I'll let you kind of take a second to do that. And write that down. All right, so every single time that we do +1 power, especially if it's like with a factorial or to a power of n, we can break it apart that way for each of them and simplify down a piece. Okay. All right, now if you got to this point, and you can get to this point in the future, you're doing good. Most of the times when you get to this point, you'll be able to see how, like, using like in behavior rules, how it converges and stuff like that. That'll be fine for you. This was just a little bit unique of an example, okay, and I didn't expect you to simplify it further from here, and that's fine. If they're both being raised to a power of n on the denominator, so there and there, you can write the whole quantity to the power of n. So n plus 1 over n to the n power. Okay. And what happens is, like, inside that fraction n plus 1 over n, you can actually simplify that down. Okay. To n divided by n is 1. 1 divided by n is 1 over n raised to the power of n. All I did was divide out. And I told you to write this identity down in a previous slide. This limit is actually equal to e. And I promise you, you'll probably never see that again. Okay, I doubt it. It'll be like in behavior rules with limits. So it should be pretty straightforward. Okay. So that limit equals e. E is approximately like 2 point something, which is greater than 1. Okay. So according to the ratio test, this series diverges. So then therefore, by ratio test, series diverges. Questions on that? I'll give you a second, write that down, and then we'll move on to the next one. Okay, another example. Test the series, or test the convergence of the series. Now, okay, if I'm asking you to test convergence, okay, I know that I taught you yesterday, like, here is that -1 to the n, and I told you if you see that, you're thinking, oh, it's alternating series test. Let's do this. And you would go through the steps from yesterday. Well, the only issue is if I consider this as a sub n, and I try to do like, I try to do the test for convergence, and then I try to take like the derivative and talk about it ultimately decreasing, like that, that doesn't work out good for me, okay? Or it's not as easy to see. So I told you, like, if you see the factorial, especially, I would be thinking ratio test, okay? So I think it's going to become very procedural here. Just going to be the limit n approaches infinity of a sub n plus 1. And remember, since I'm taking the absolute value, the -1 to the n, that doesn't matter. So that goes away. Okay. And it's going to be n plus 1 factorial divided by 100 to the n plus 1. So there's your a sub n plus 1. I'm going to go ahead and do same change flip. Because we're dividing by a sub n, I'm going to do same change flip. And it's going to be 100 to the n over n factorial. Okay. Now we got to simplify, figure out what the limit is, compare it to 1, and then we have our answer. Okay. And remember what I said, the n plus 1 powers and the n plus 1 factorials, you can always split apart. Like this is the same thing as 100n times 100 to the first. N plus 1 factorial is the same thing as n plus 1 times n factorial. Okay. And then the n factorials cancel. The 100 to the n cancels. And I'm left with the limit as n approaches infinity of the absolute value of, on top I'm left with just n plus 1, and on bottom I'm left with, what am I left with on bottom? 100. Okay. Now, as I take the limit to infinity, all right, of n plus 1 over 100, if you do your n behavior rules for rationals, you got a power of 1 on top and a power of 0 on bottom, so you got a higher power on top. That limit is equal to infinity. And infinity is greater than 1, so therefore, by ratio, test, series diverges. Any questions on that? That wasn't bad, right? So that's the ratio test, and that's as crazy as I think you're going to see it, especially with kind of the time restraints we have now. There is one more thing on here that I think is mandatory, because I think the root test goes with ratio test, and I got 2 slides with that. And then everything after this, I believe, based off of the notes, that it's not the most mandatory thing in the world, but I'm still going to teach it. Okay. All right. The root test. The root test and the ratio test, in my eyes, are the same exact thing. They're just approached a little bit different. Okay. So your ID for this one, how you recognize it with a given series to use the root test, your ID, is if you have the summation of a sub n, and it's just some quantity. It can be some crazy quantity, all to the power of the n, all to the power of n. If you see that you have some function all raised to the power of n, then the root test is the best way to approach it, which is pretty much the ratio test. It says the same thing. It says the limit as n is approaching infinity of the nth root of the absolute value of a sub n. That's what it looks like. If that limit is less than 1, it's absolutely convergent. And if that limit is greater than 1, then the series a sub n is divergent, and if it equals 1, it's inconclusive. So if you're given this series, if I set it up like this series, or I'm sorry, this limit, and it's equal to some number that's less than 1, it's absolutely convergent. Okay. So we're about to do, I got one example of that because it's not the most tested thing, but it does go with ratio test. And then I'm going to move on to some optional stuff. Okay. So questions on that? Everybody got that written down? All right. Then our next slide. Okay. Look at the series that we're given. All right. The series is, we got a whole mess of stuff going on. I mean, it's not the most craziest thing, but it's 2n plus 3 divided by 3n plus 2. All right. We have something going on, and the whole thing is being raised to the nth power. If you see a series where the whole thing is being raised to a power of n, then you're thinking that's an application of the ratio test. It's called the root test. How the root test works is if you see that, you're going to set it up this way. You're going to say the limit as n approaches infinity. All right. Now, the setup is going to be the nth root of the absolute value of a sub n, which is 2n plus 3 over 3n plus 2 quantity to the nth power. Okay. Now what happens is, the point of the root test and why it's helpful for this situation is if I take the nth root of some quantity all raised to the nth power, it crosses it out. Boom, boom. Then what I'm left with is the limit as n is approaching infinity of the absolute value of 2n plus 3 over 3n plus 2. Okay? And that is just a basic rational. We know how to take the limit of n as it approaches infinity for this. It's not the craziest thing. The powers are the same on top and bottom, so we take leading coefficients. This is equal to 2/3. 2/3 is less than 1. So therefore, absolutely convergent by root test.
Wait, so does it matter that when you raise the a sub n to the power of n that it was inside the absolute value?
No, it does not matter.
Okay.
Yeah, I had the same question when I started was doing this and learning this, and no, it does not matter. In fact, some let me see here. Yeah, some teachers write it on the outside of the absolute value, but I don't, because that's not what it says. So, but no, that does not matter. So, yes. Any questions on that? Root test? Root test is not hard. When I tested it on the test, it was like 1 or 2 questions, and it was give me points. Okay, so I don't want that to stress you. But how do we feel about the ratio test? Ratio test, okay. You see how the steps are very much the same. Okay. So that's a great way to test convergence for whenever you have factorial in the problem, or power of n really in the problem as well, but mostly factorial. Okay. Now the remainder of the notes is talking about how to find the interval of convergence, which we've talked about with the power series, and you can even see in this slide as a power series. We talked about how to find the interval of convergence using the ratio test. That is another big important thing with the ratio test. So I'm going to go over that real quick, do a couple examples, and then we should be done. So then I got a rather few amount of examples on that. So we'll just see how it goes. Okay. All right. Now recall that this function as a power series, we got 1 over 1 plus x squared, which is the same thing as 1 over 1 minus negative x squared. Okay. If I were to represent that as a power series, we've done this a bunch of times. That's n equals, don't do that, n equals 0 to infinity of negative x squared to the n, which if I asked you to simplify, which we're not having to really worry about in this slide, you would simplify it to negative 1 to the n x to the 2n. Okay. No big deal there. But what I asked you to do in the past was to identify the interval of convergence of this power series. Okay. And I told you to do that is you want to take whatever the quantity is, pretty much whatever this quantity is right here, and you're going to do the absolute value of that is less than or equal to 1. I'm going to say to do the interval of convergence, we did the absolute value of negative x squared is less than or equal to 1. Okay. And then the absolute value was the same thing as, well, taking the absolute value is going to make this positive x squared. And that's the same thing as doing between 1 and negative 1. Now, I also chose this slide because it was a question that had come up in our class, and something I talked with some people later on, is because now if we were to get the x by itself to figure out the interval of convergence, we would take the square root of everything. And then we ran into the issue where we take the square root of negative 1. And I asked another teacher, and I was like, okay, so what does that do? I mean, we can't take the square root of negative 1. And they said, well, that does not. So pretty much they said to ignore the negative. It does not affect the interval of convergence in that sense. The square root does not affect it that way. So I was like, okay. So it's still going to be between negative 1 and 1. Okay, they said the square root's not going to affect it with the negative. So I was like, okay. So that's my interval of convergence. That's what we discussed. Okay. The center in this case was at x equals 0. and it was between -1 and 1. Okay. So we're going to dive deeper into that with the ratio test to identify intervals of convergence. And the biggest thing, and this is something I purposely left off, is we always have to consider if we include the endpoints or not. Sometimes the endpoints of the interval of convergence work and sometimes they don't. So we always have to test them. Okay. I left that off with the power series part because I wanted to wait to get to the ratio test part. So we're going to do a few examples of that. All right. So we got 1, 2, 3, 4. I mean, I'm going to do all these examples and you can stop at any point that you start to feel comfortable. But anyway. Okay. Now, it says that any power series, all right, in this form, that's the form we talked about power series in, is going to converge at x equals a. All right, and if it's centered at 0, then that's just equal at 0, right? So any power series is always going to converge at x equals a. The reason is because it makes this quantity right here equal to 0. And if that's equal to 0, then it's just going to converge to 0, okay? But there's 3 cases that can happen for intervals of convergence when we're centered at a, okay? There's 3 possibilities. The first one is the one that we're most used to seeing, okay? There is a positive number r.
Your audio just cut out, by the way.
Oh, okay. Thank you for letting me know. Is it good right now?
Yeah, your audio is good now, but
Okay, cool. So there's 3 cases that we talked about for the interval of convergence, okay? Go ahead. Oh, no. Oh, I thought someone was asking me a question. Okay. So there's 3 cases. The first case is the one that the only one that we've dealt with, okay? Where there's some positive number r, which is our radius, which most of the time for us was equal to 1, such that the series converges when the absolute value of x minus a is less than or equal to r, okay? Where r, oh, I already said it, where r is your radius of convergence. Why is it doing that? A. And then the series may or may not converge at the endpoints. Okay, we're going to have to test this.
Mr.
All right.
Forward, did you say this is the stuff that we need to know, or are you just teaching?
I'm just teaching it from here on out. So we stopped at root test because here's the thing. All the examples we saw before were just in the series. So we were just testing to see if that specific series was convergent by the ratio test or not. And now we're incorporating power series into it. And now instead of just having n, we're going to have x as well. And we're going to have to figure out what x values is going to make it converge based off of the ratio test. Okay. Now, in case 1, this is going to happen when we're taking the limit, it's going to be a rational where the numerator is equal to the denominator in power. And I'll show an example of that as we get to it. Okay. The other cases is going to be the series is going to converge for every single value of x. This is whenever your numerator is going to be less than your denominator. Again, I'll show that in the next few examples. And then the last case is the series is going to converge just at x equals a and diverge everywhere else. That's whenever your numerator is greater than your denominator. Okay. So let me show examples of all these and show how the ratio test is used to figure out this interval of convergence. Okay. All right. Number 1, it says find the radius and interval of convergence. Okay. Now, the ratio test is extremely helpful for doing this. The ratio test is the way to do this. If I want to figure out where the interval of convergence is, it's whenever the ratio test is less than 1. Okay? So I'm going to set up the ratio test. I'm going to say the limit as n is approaching infinity of the absolute value of. it's going to be a sub n plus 1 divided by a sub n. So I'm going to go ahead and put x to the n plus 1 divided by 10 to the n plus 1. And we're going to multiply that by 10 to the n over x to the n. Okay. Okay. Now, just to save some room here, I'm going to go ahead and start crossing some stuff out. Okay. 10 to the n plus 1 and 10 to the n. All right. Remember, that's just going to be 10 left over here, and the 10 to the n's cancel out. Okay. That's because you can break apart the 10 to the n plus 1 to 10 to the n times 10. Okay. Same thing right here. The x to the n plus 1 and x to the n. I'm getting rid of the x to the n's, and I'm left with just x right here. That's because, again, we can split apart x to the n plus 1 to x to the n times x. Okay. So what this reduces to is the limit. As n is approaching infinity of the absolute value of what we're left on top with is x to the n plus 1 over, what's on the bottom? 10n, is that right? Okay. Now, I am taking the limit of this as n is approaching infinity. N, not x. N is approaching infinity. So, because the powers of n are the same on top and bottom, we take the leading coefficient. The leading coefficient is x over 10. So what this is equivalent to is the absolute value of x over 10. That is what the limit is. Now, if I want to know what x value I need for this to converge, by ratio test, this value must be less than 1, therefore satisfying the ratio test. Okay? So, if I were to set this interval up, that would be x divided by 10 is less than 1 and greater than -1, and simply solving for x, that radius of convergence is between 1, I'm sorry, I wrote that completely wrong. The interval of convergence is between 10 and -10, just multiplying by 10. Okay, that is my radius. So any value between -10 and 10, all right, any value between -10 and 10, if I plug it in for x into this series, that series will converge. Okay. Now, the only thing is do we include -10 and +10 in that interval? So once we find the interval of convergence, we have to test the endpoints to see if we include them or not. Okay. And it's real simple. All you do is just plug in -10 for x, and you plug in 10 for x, and you just see if they converge or not. We're just testing points here. So I'm going to start with, let's start with x equaling 10. So that's going to be the summation n equals 0 to infinity of, now it's just going to be 10 to the n times n, 10 to the n, okay, over 10 to the n. Okay. Now, if I'm trying to check to see if this converges or not, 10 to the n's cancel. And I'm left with just the summation of n. If I take the summation of n from 0 to infinity, what's that value going to be equal to? Just infinity. It's infinitely getting bigger. N diverges. Okay? So we do not include 10 in the interval. Okay? All right. So let's also test to see if -10 works. So we're going to do x equals -10. And I'm going to say the summation n equals 0 to infinity of -10 to the n times n over 10 to the n. Okay. Now, I can still simplify it the same way I did previously, but I have to take out that -1 to the n. I have to take out that alternating piece. So this is actually equivalent to the summation n equals 0 to infinity of -1 to the n, 10 to the n times n over 10 to the n. So the 10 to the n's cancel. And what I'm left with is -1 to the n times n. Okay, and that is an alternating series. So if I wanted to test to see if this series converges or not, I can do the alternating series test. So I'm going to follow my steps. I'm going to say step 1, I'm going to do the test for divergence. And if I do that, I'm going to do the limit as n approaches infinity of a sub n, which in this case is just n, and that equals infinity. So therefore, it is divergent. Okay. So in this particular example, we do not include either 10 or -10 because it would diverge. So this is our final answer. This is the interval of convergence. The radius is 10. Okay. Does that make sense? That's all this is going to be. All you're doing is the ratio test with x included, solving for the interval of convergence, and then just testing the endpoints. And that's it. That's it. Okay. So any questions on this one before I move on? The rest of the examples are just like this. So if you didn't get this one 100%, the countless more examples I have should help. Okay. So we keep going. All right. N to the n factorial times x to the n. I'm trying to test, first of all, like I'm trying to figure out what the interval of convergence is. What does x have to be? What does x have to be in order for this particular series to converge? So we're going to do a ratio test, okay? Because we got x to the n, it's a power series. We can do the ratio test with this. So I'm going to say the limit as n is approaching infinity, and doing the ratio test is going to be a sub n plus 1. So that's n plus 1 factorial. Oh, that's ugly. N plus 1 factorial times x to the n plus 1, and then divided by a sub n. And this is not going to be same change flip because it wasn't irrational at the beginning. So this is just going to be n factorial times x to the n. Okay. We're going to simplify that down and discuss what the radius looks like. Okay, what the interval of convergence looks like. So same as before with ratio test, I can simplify this n factorial and this n plus 1 factorial to just n plus 1 on top because the n factorials cancel. The x to the n plus 1 and x to the n is going to cancel to just x on top. So what I'm left with is the limit as n is approaching infinity of the absolute value of, all we have is just n plus 1 times x. Okay. Now, what is the limit of that going to be as I approach infinity? Well, in this particular example, it's going to be equal to infinity, right? Because if I plug in higher and higher values, all right, n for n, it's just going to keep getting bigger and bigger and bigger. The limit's going to go on to infinity. All right. Now, if that's the case, if you get it, and if you think about this, this is n plus 1 times x over 1. There's a higher power on top, so we would say this is like being, the numerator is greater than the denominator. And if you go back to this slide here, that's like having case number 3. If the numerator is greater than the denominator, it's only going to converge at one value, x equals a. So in this particular example, it is only going to converge. It is only converging at x equals a. And in this case, since it's just x, it's not x plus or minus something, it's only going to converge at a equaling 0. Because think about it, if I plug 0 in for x, that whole quantity becomes 0, and then obviously the sum will converge. Any other value I plug in for x, that thing's going to diverge to infinity. So my interval of convergence is just 0, my radius is equal to 0, and we're good to go. Okay? So whenever your limit equals infinity, there is only one value that can work, and that's just the center. Okay.
Wait, is a the same thing as x?
Well, no, because remember well, yes, but it's this form right here. Remember we have c sub n times x minus a to the n. So if it's just x as the base, then a is equal to 0. There's just no shift in the center, that's all. So this is the same thing as my center.
So it converges there?
Yes, so whenever x is equal to 0, that is the only, I see what you're saying now. Whenever x is equal to 0, this is the only place that it converges. It only converges whenever x is equal to 0. There is no other x value that works. Absolutely. Okay. That's like case number 2 or number 3 on that list. Okay. I got a few more. Few more. Y'all doing good. Okay. Ratio test again to figure out what the interval of convergence is. Okay. Now this is an alternating series piece. And remember, when I'm doing ratio test, the alternating series goes away because I'm taking the absolute value. So let's think about how this limit looks. It's the limit n approaches infinity, absolute value of a sub n plus 1, so that's x to the 2, and then, dadgummit, why is it doing that? 2 to the n plus 1, so that's n plus 1 instead of n, over 2n plus 1 again. Dadgummit. Okay. Same change flip, 2n over x to the 2n. Okay. Any questions on that? Okay. I should probably write out the next step. I'll say the limit as n is approaching infinity. What's going on here is that this 2 and this 2 can cancel. And as far as the x's go, I got x to the 2n here can cross off with x to the 2n here. And I'm left with just an x squared, because if I distribute the 2, I'm left with just an x squared right here. Okay, so I'm left with on top x squared n, and on bottom I'm left with just n plus 1. Okay, if I were to expand out that x to the 2n plus 2 power, the 2n power would cancel out and I'm left with x squared. Okay. Now, if I'm taking the limit of this as we approach infinity, the numbers of the leading coefficients here are what we're going to take because it's the same power on top and bottom. So this limit is equivalent to the absolute value of x squared over 1. And if I want to figure out where this is convergent for x, I got to figure out where it's less than 1. So I'm going to solve that. I'm going to do x squared is greater than -1, less than 1. Remember how we said taking the square root doesn't really affect that. So x is less than 1, greater than -1. Okay. So it's between -1 and 1 that if I plug that in for x into that series, this series is going to converge. I just have to see if the endpoints also converge. Okay. So we're going to check both endpoints. So I'm going to say, all right, we're going to check whenever x is equal to, I'll start off with 1. Okay. That's going to be the summation n equals 0 to infinity of -1 to the n plus 1. Instead of x, we got 1 to the 2n all over.
Your audio is pretty bad right now.
Sorry.
It's better now.
But anyway, all I did was plug in 1 for x. Okay. Now, 1 to, if I'm trying to figure out this convergence right here, 1 to any power is what? Just 1. So that pretty much goes away. 1 to the 2n is just 1, so that goes away. And what I'm left with is -1 to the n plus 1 over 2n, which is an alternating series. If I want to test the convergence for an alternating series, I'm going to do the test for convergence for an alternating series. The first part of which is to do the test for divergent and discuss the limit as n is approaching infinity of a sub n, which is 1 over 2n. All right. And that definitely equals 0, so we're good there. And the other piece is to do to see if it's ultimately decreasing. So for step 2, I'm going to look at f prime of x, which the derivative of 1 over 2 to the n is -1 over 2n squared. And that's always negative. So it's always decreasing. So we're good there. Okay. And that's just from the test for alternating series from yesterday. So in this case, we do include 1 in the interval. So now I'm going to test x equals -1. And that's the summation n equals 0 to infinity of -1 to the n plus 1. And now -1 to the 2n all over 2n. Okay. Now the -1 does not simplify out like it did last example with the 1. Okay. But if you notice, I have 2 common bases here, so being multiplied, so I can combine their powers by adding them. Okay. So that would be like having -1 to the 3n plus 1 over 2n. And if you notice, that's an alternating series, and it's the same pretty much alternating series as the previous one. So it's going to follow the same exact steps as before for testing it. So yes, this is also convergent. So this example, both endpoints are included. Does that make sense? Okay. Any questions on that one before I move on? All right, y'all doing awesome. I got 3 more, and again, if you don't like it, you don't like it. It's okay if you don't care about the radius of convergence with ratio test. As long as you understand the ratio test, that's perfect for me. And this is practicing doing the ratio test, so that's good. Okay, this one's not so bad. So again, we're just gonna do the ratio test, same as before. Y'all become experts at that by now. L, a limit, n approaches infinity. I'm gonna do a sub n plus 1. So 10x to the n plus 1 over n plus 1 factorial. I'm gonna multiply that by n factorial over 10x to the n. Questions on that? All right, let's cancel the usual. N factorial, n plus 1 factorial becomes n plus 1. 10x to the n and 10x to the n plus 1 is just going to become 10x to the first. Okay, the n plus 1s, or the 10x to the n is just canceled. Okay, so what I'm left with is the limit n is approaching infinity of the absolute value. On top I have 10x, and on bottom I have, what do I have on bottom? N plus 1? All right. Cool. Here is where it's kind of interesting. So think about it. If I'm taking the limit of n as we go to infinity, we have n to the first power on bottom and no n's on top. So we have the numerator is less than the denominator. Okay, so that limit is equal to 0. All right. Now, what that means is, like, notice how x didn't transform over to this point right here. Okay, what that means is how's the best way to say this? The interval of convergence is equal to negative infinity to positive infinity. What that means is no matter what value I plug in for x, the limit will always be equal to 0, meaning it would always converge. Okay, so interval of convergence converges for all of x. Is it? The radius is just infinity. There is nothing you can plug in for x that's not going to make that limit converge. So there is no step of doing the absolute value of something less than 1 because there is no x to solve for. Okay. Not bad, right? So that was case number 2, when we can have it to where the interval of convergence is infinite. Any value we plug in for x is going to make it convergent. Two more. This next one's pretty quick too. I didn't even ask. Any questions on that one before I move on? Do what?
That Lisa Zotto.
Okay.
Mackenzie.
All right, here we go. This next one, let's practice the ratio test one more time. We're talking about intervals of convergence. We're going to do the limit.
You haven't even been using it. Leave it.
N approaches infinity. We're going to have n plus 1 factorial x plus 1 to the n plus 1 divided by n factorial times
No.
x,
Right whenever you see it, you want to use it. But any other time, you don't use it.
x plus 1 to the n. So we got a sub n plus 1 divided by a sub n. Okay.
No.
If we simplify that down, the n factorial and the n plus 1 factorial goes to n plus 1 on top. The x plus 1 to the n and the x plus 1 to the n plus 1 goes to x plus 1 on top. So what we're left with is the limit as n is approaching infinity of the absolute value of n plus 1 times x plus 1.
I will put the whole thing in my mouth, and I'm not scared to. I dare you.
So anyway,
Hey.
if I
Never mind. Okay. Never
I
mind.
take, you sure?
Yeah, I'm sure. I was just going to comment on the ambient noise coming from someone else's. But
Oh, okay. Let's just try
I'm
to.
guessing if they could hear you, they probably would have muted themselves already. It's going to be like,
Yeah, that's okay. We're almost done. It's okay. Anyway, if you take this limit to infinity, you got the numerator is greater than the denominator. It pretty much, because it's all over 1, so that's going to go to infinity, meaning that the limit is always going to be greater than 1 unless we plug in the center. So in this case, the interval of convergence is only at x equals -1. It's what's equal to that makes my center equal to 0. Okay, so the sum goes to 0. Any other value for x is going to make that grow exponentially, and diverge. Okay. Is there any questions on this particular situation right here?
Oh.
All right. I got one more example, and we'll get through this one quick, and then we'll call it for today. So, all right. If your dog's barking, it's okay to mute your mic. All right. I can't. Live videos. Okay. This last one's a good one to end on. So we're going to do the summation n equals 0 to infinity. Oh, I'm getting hot. All right. n equals 0 to infinity of a sub n plus 1. So that is x minus 3 to the n plus 1 over 2 times n.
Your audio got kind of quiet again.
Okay, thank you for okay, cool. So then times,
Why'd you write the summation?
oh God, I don't know why I did that. Oh boy, I'm getting fatigued. There we go. Times x minus 3 to the n. We're going to simplify everything down like we usually do and solve this bad boy up. So the 2's cancel. The x minus 3 to the n and the x minus 3 to the n cancel, and I'm left with x minus 3. You see how very procedural it becomes. We got the limit. N is approaching infinity. On top, we're left with x minus 3 n. On bottom, we're left with n plus 1. So if I take this limit to infinity, all right, we got the leading powers on top are the same. So we're going to take the leading coefficients, which in this case is x minus 3 and just 1. So I'm left with the absolute value of x minus 3, and I want to solve for x whenever it's less than 1. Okay. So that's the same thing as x minus 3 is less than 1 and greater than negative 1, and solving for x, that's less than 4 and greater than 2. Okay. So in this case, my center is at 3, and we can even see that in our power series at the beginning. But my interval of convergence, the values that work are between 2 and 4. I just got to see if 2 works and if 4 works. I think this is, so I'm going to test the endpoints, and I'm going to do x equals 2 at first. And let's plug it in. So I got the summation n equals 0 to infinity. Oh, not x, but 2 minus 3. And wouldn't you agree that 2 minus 3 is just negative 1 to the n over 2n? Okay, all I did was plug in 2 for 3, or 2 for x, and 2 minus 3 is negative 1. Okay. All right, so test for convergence. And actually, guys, didn't we do this exact one earlier? Yeah, didn't we do negative 1 to the n over 2n? Well, it's an alternating series, okay? So we got 2 steps here. We got to do the test for divergence, and that works. And we got to see if it's ultimately decreasing, and that works. Yeah, we did this exact one earlier whenever I was testing endpoints before. I'm pretty sure. So in this case, 2 is actually included in the interval because it's convergent at 2. Let's see what happens when I plug 4 in. It's going to be the summation n equals 0 to infinity of, now it's 4 minus 3, which is positive 1 to the n over 2n. And like I said before, 1 to any power is just going to be 1, so that cancels out. So what I'm left with is the summation n equals 0 to infinity of 1 over 2n, and that is a harmonic series. And what do we know about harmonic series? They diverge. So in this particular example, the endpoint 2 would make it convergent, but 4 would not.
Wait, how do you know that it's a harmonic series?
I can split this apart to 1/2 times 1 over n. I can take the 1/2 out as a constant, and I'm left with just 1 over n, and that is a harmonic series.
So you can put the 1/2 like outside the summation?
Yeah, and even if you didn't take it out of the summation, the 1/2 is just a constant. It doesn't affect the convergence of the 1 over n.
Oh, yeah.
And 1 over n is just a harmonic series. So in this case, just 2, but not 4. Okay.
But if you had like 1 over n squared, that would be convergent. Right?
Yes, if this was 1 over n squared, you would say convergent by p series. Yeah. Yeah, and I'm going to do a video lesson later this week that's completely optional on the comparison test, and you'll see how harmonic series is very, and p series is very helpful for comparison tests. But anywho, that does it as far as my lesson goes. Is there any questions before I end the video that we can help the viewers? No, I'm gonna go.
Yes, there is. I have a question about the AP exam. So
All right.
I know you probably don't know a lot, but I'm going to. Is it fair to assume that because we're doing this at home, if it is, like whatever it is, it's probably going to be calc active because they have no real way of stopping us from using our calculators? Would you think that's what it would be?
I would. That makes logical sense to me. Yes. But before I talk more about the AP exam, I'm going to say bye to the viewers. I'm going to say, okay, hopefully that makes sense. Good luck. Bye.